All right, why don't we kick things off here? Welcome everybody to this webinar hosted by the MSD Community of Practice on generative agents, a new frontier for representing human actors and their behaviors in MSD models. As we start off here, we did also just want to lay out some webinar ground rules. We, of course, expect all conversation today to be considerate, respectful, and collaborative among our colleagues on the line. We want to maintain a supportive and positive environment that fosters and welcomes open questions and input. So we're glad you're here with us today. We also did want to note for everybody's awareness that this webinar is being recorded. So please make note of this. All right, so first off, I'm aware that there may be several here who are new to the community. So first off, what is multi-sector dynamics? We're a community of practice largely consisting of researchers and modelers based out of national laboratories and universities across the United States, but with a growing presence in Europe and beyond. And as a community, we define multi-sector dynamics as the study of how complex built, natural, and socio-economic systems co-evolve in response to change. And as you can see on the figure here, these changes pertain to both climate-related influences, so droughts, floods, wildfires, and so forth, but can also pertain to non-climate related influences. So thinking about things like population dynamics, technological change, and so forth. And as illustrated in this figure, from the MSD vantage, these changes are then modulated through a host of interacting systems and sectors and result in outcomes of societal interest. So towards that scientific vision, the MSD community of practice represents an effort to accelerate development of needed foundational capabilities in human Earth system science through open science and growing a transdisciplinary workforce. If you're interested in learning or getting involved in either the community broadly or any number of working groups that are kind of sort of the heartbeat of the community of practice, you can visit our website via this main QR code on the left here. Some of the working groups are represented here today. We have, I run the Human Systems Working Group, Stefano on the line leads the AI/ML one, and Vivek leads Uncertainty one. And so those are just a snippet of the working groups that you might get involved in. We also have a pretty active community forum on LinkedIn where we post webinars such as these, share out interesting research papers, link to career opportunities and such. So I'd highly encourage you to join our LinkedIn community via the QR code in the lower right. All right, so that brings us to the topic of focus today, which I'm very excited to be tackling. We'll be highlighting this topic of generative agents, a new frontier for representing human actors and their behavior in MSD models. First up today, we'll be hearing from Chen, who's a professor at Dartmouth College, who will share her work on utilizing generative agents to realistically simulate customer decision-making in dynamic energy operations. Then secondly, we'll hear from Yongchao Zeng, a researcher at the Karlsruhe Institute of Technology, who will describe a new simulation system called HOPES that enables users to explore simulations of social ecological systems and also allows sort of model users to take on simulated stakeholder roles in the model itself. As just a bit of context setting here before we hand it over to our speakers, one of the major goals or themes of MSD research is tackling this question of how human actions, ranging broadly from short-term individual consumer actions to long-term societal or institutional transitions, can be effectively and dynamically represented in multi-sector models. A strategic initiative towards this end has been this introduction of a new human systems typology for characterizing how human actors and actions are represented in the wide range of models that are applied for MSD research. And this can range from anything from, say, an agent-based model of a domain-specific system to, say, a large-scale coupled human Earth system model of, say, like the global economy. In parallel to these efforts over the past few years, focusing on human representation in our MSD models, we've seen this explosion of research progress, largely coming from the AI/ML computer science community in this arena of generative agents. In this literature, generative agents are defined as computational software agents that simulate believable human behavior within these digital environments. And these agents are essentially instantiated and simulated via strategic prompting of a foundational large language model. So here I'm just showing one of the, if not the sort of seminal paper that introduced these generative agents in a sandbox environment. You can think of something like the Sims game. And this was from a group over at Stanford. And here you can see from this Google Scholar screenshot that I grabbed just this morning that the preprint of this work that was only published 2 years ago now has on Google Scholar. So this is just to give you an appreciation for sort of the speed and scale at which this world of generative agents is evolving. So given these rapid developments in this world of generative agents, a major question for us in MSD and the Human Systems Working Group is thinking about what applications these agents might have for modeling human behavior, human action in MSD models of interest. And as it turns out, as we looked into this, many people are already starting to think about this broadly in the community. So this is just a sampling of papers that I pulled from the literature that apply generative agents towards topics either central to or intersecting with MSD core interests. And as luck would have it, 2 of these papers, the top one here and the lower left, are from our 2 speakers today, who will be sharing more on their efforts in this regard. So hopefully that provides us some context. And without further ado, I'd like to hand it over to our speakers. Just to give you a sense for organization here, we're going to first hand it over to Chen to share her work. Then we'll move on to Yongchao. We'll save questions and discussion for the end here. So if you have any questions for the particular speakers, save that for then. You can either, when that discussion time comes, like place your questions into chat or raise your hand on the Zoom feature when we move into that. So with that, I'll hand it over to you, Yusung.
Yeah, thank you very much. Thank you for hosting this nice opportunity for us to share our research. And today I would like to present my latest progress about the behavior generative agents for energy operations. A little bit about my background. So I received my PhD from the electrical engineering. I focus on the power system at Cornell University. And later I focus more on the electricity market, energy pricing at the Stanford Graduate School of Business in my postdoc. So now I just joined Dartmouth College as a system professor. This research of behavior generative agent is also a joint work with my postdoc mentor, Xu Kuang and Omer Kladuman from Stanford. So at the very start, I will just give a broad research overview, very quick, about some topic I've been working on. Then I'll get into more detail about the behavior generative agents specifically for energy operation work. So in my previous research, I focused on all the renewable uncertainties, the dark curve issue in California, and will propose new pricing method that is like a rolling window, very close to the model predicted control flavor. And we try to figure out what's the pricing strategy under uncertainty. And we also look at the storage problem, and I figure out a complexification condition to operate storage in a more simpler mass model. And this is very related to today's talk, the distributed energy resource. So DER include rooftop solar, electric vehicle, home battery. All those resources are ubiquitous in our energy systems. And we are thinking about how to schedule all those resources more intelligently. And with all those research, I received the Outstanding PhD Thesis Award in IEEE PS Society. And I also received 2025 Amazon Research Award for the AI agent research. That encouraged me to move forward from here. So a brief background about the AI agent for energy operation research. I focus on all the rooftop solar, electric vehicle, home battery. The question is how to operate all those energy devices. And naturally, we have all those like smart home, IoT, information of technology that helps. But more importantly, actually, we have all the human user. Some people will prefer energy efficiency. Some people prefer green energy. Some people may just want to say, I want to have backup. I want to have energy security. So different customers have different preference. And in this work, we hope to use AI agent as an energy customer simulator. And back to Jim's introduction, this work is also inspired by Stanford, Park, and Michael, their group. So when they simulate each small character in their virtual village built online, each small character powered by large language model, and they have their daily routine, like wake up and catch up packing or begin their working day. So all those daily routine, people feel like I cannot distinguish if those routines are provided by computer or provided by real human. So this raises a lot of discussion in economic society, saying maybe we can have a human simulator, and how can we use that? So for me, because I'm a power system engineer, and I'm thinking when you wake up, you open your lights, when you're cooking, you use some electric devices, your energy usage behavior and your daily routine are coupled strongly together. So I'm thinking maybe those kind of agents can help us understand energy customers specifically, how those customers would like to use their home battery, electric vehicle, how do they prefer, what's the customer preference under different conditions. So that is like the background motivation here. We want to bring human behavior insight to energy operation. And specifically, this is the framework I built to make this agent work. We built a thought, action, reflection journal, those kind of workflow. And currently I put it in the experiment of home battery management under dynamic pricing. So the experiment I run is based on we give a prompt to the agent to run a home battery, and we evolve every day. It is a dynamic decision over time. So specifically, the experiment we run is we give a home battery to an agent to use a home battery over 20 days, and we change the price every day. We also told the agent saying the electricity price will be dynamic, changing maybe from $5 to $10. Every day you will see different price. Then please let me know how are you going to use your battery. So we ask the LLM agent to go through a procedure like first give a thought, elaborate your thoughts of the experiment and the current state, and then take your action. You want to charge your battery, discharge, or do nothing, and do a reflection. So does your action help your goal, the pros and the cons of your current state, and then write a journal, document your thoughts, and help you refine your strategy for the rest of the experiment. So we will store the journal into the memory and carry the memory over day. And every day we will give them different price. We will tell them what's your state of charge, how many energy stored in your home battery, and what is your historical action, and what's the historical information you have. And you also bring the memory carrying every day. So we also design different persona, like we want to see different customer, how would they operate battery differently. So this is a framework. And let me give more detail about the persona part. So we have different customer. We want to use your AI agent to representing different customers for energy customer. And specifically, I start with a thinker customer. I say you are a PhD. I ask a large language model to role play it and to prefer logical thinking, analyzing data, and do optimization. And I also ask a large language model to role play an actor. They love intuitive thinking and they are more emotionally driven. And we also have someone in between. I ask GPT to role play a grandma. You are a realist. And although you don't have formal education, but you have excellent understanding because of your historical business running experience. So this is a very interesting matrix. And this comes from the MBTI thinker and the feeler dimension. So basically we have thinker, feeler, and we have something in the middle. I want to say how large language model would role play different persona in those energy management experiment. So let me give an example. Like I use Llama to role play PhD and go through the thought, action, reflection journal every day. And at day one, I told them, today your price is $5, your energy level is 0 for your home battery. And what are you going to do? So the thought is, Llama say, given the initial condition, we start with an empty battery, relative cheap price, and we aim to optimize outcome. So we will utilize this factor effectively, and they decide to charge the battery. And by charge battery, they will pay for the energy. And they do a reflection, choose to charge, help the goal since we start from 0 charge. And the pros, including take advantage of lower cost upfront, potentially save money over expensive day. And the cons could be they actually cutting funds early without knowing future price. So very logical thinking, and they carry all the information precisely. The journal they write is like day one, the journal charge battery when empty due to the price. And it is like now they know battery after charging will increase from 0 to level 1, and they will reassess tomorrow's condition. And when they move to day two, they know day two, now they have a different price, but unfortunately the price is still $5. They didn't change that much. And in my more experiment, I also give it maybe $10 and a higher price to see what happens. And they try to say like, they see the price is 5, they estimate the average price should be, they give a threshold, and they choose to do nothing for the battery because they think this is not the best time to use the energy for some way. And the journal is like day 2, consider the low price. I choose not to charge or discharge to avoid suboptimal decision. So we can see PhD is doing optimization, data analytics. So that's a simple example. I have many examples of this role play different persona, but let me get into some practical insights. So this is data from the home. It's not a home battery. It's a very large battery running by Tesla in Australia. And we take their data in this March. And we can see the blue curve, battery charging, when the black curve, the price goes low. So left-hand side is battery power, right-hand side is price of electricity. So we can see when price changing dynamically, battery try to charge at low price, discharge at high price. It's like by charge, they pay for the energy, discharge, they get paid, and this is how the profit comes in. So I want to say large language model capture this revenue stream with this simple experiment when role play PhD. And let me try to catch with a mathematical benchmark, because everybody are asking, can you believe this? How can we trust this large language model? And what would be a good benchmark? So one option is we can have some math benchmark. This experiment can be formulated into a stochastic program. The objective is like we want to maximize battery profit. So the pi is like the electricity price that's changing every day, and the U is the net output. If it's positive, they discharge. If it's negative, they charge. And they just maximize the expected profit when battery try to charge, discharge. And they have constraints. So S is the energy stored, and the S is changing with the U charging, discharging action. S also have upper bound, lower bound because the storage have finite storage capacity. So this math benchmark can be solved by dynamic programming, and we can figure out the optimal solution, what it is. So let me give more detail about the solution structure. On the top is optimal policy. On the bottom is a greedy policy. On the left-hand side, this is accumulated reward over those 20-day experiment. On the right-hand side, this is battery state of charge over 20 days. What is their action under those different policies? So the optimal policy and the greedy policy from day 0 to day 10, they all choose to buy low, sell high. So when the price is low, they charge. When price is high, they discharge. That is their principle for the optimal action. And by the end of the day, because at the end of the 20-day experiment, we will remove the battery from the customer, and any energy left won't have any value. So in the optimal policy, they will choose to sell everything, sell all the energy so that they can make the maximum profit. But the greedy policy don't see that. Greedy policy is very short-sighted. They don't see the future. They make decisions just based on the current price. If it's low, I buy. If it's sell, if it's high, I sell. It's very intuitive, short-term greedy policy. So these are two benchmarks. And when I try to use large language model to run a simulation, I find thinker's action very close to the optimal policy, and the failur's action close to the greedy policy. That is very interesting. Like we can use some mathematics benchmark to understand large language models' behavior in a dynamic environment. So let's take a closer look. For the right-hand side, we can see the energy state of charge, and we can see buy low, sell high at the beginning for everyone. And by the end, the red curve is dynamic program. The optimal policy sell everything. And we can see blue, the thinker, and the realist, the grandma, they are trying to sell everything. And at the top, the greedy policy is buy low, sell high all the time. And we can see the green curve, the failure, is very close to the greedy policy. So their action are very close to those like mathematical benchmark. That is very interesting. And I also want to say all those results works after the reasoning model. So before, actually last year, all my experiments failed. And I take the question, large language model can be a human simulator, but last year, all my experiment just shows big variance of large language model output. They don't follow the constraint of the state of charge. They don't know, like, they don't understand the problem when I prompt it. But this year, all those reasoning model can capture a very well solution for the rational behavior. And this year, I do see a little bit of variance, like some model are good at role play different customer. Some model are more better in do a more rational thinking to compute analytically. So we do test a different price environment from easy to hard, and we find the large language model behave more optimal and less variable in simpler market scenarios. So this is a terminal reward, and they get higher reward, less variable, and this makes the model more credible when we try to run experiment with them. And more importantly is the preference cluster we find. So basically, the left-hand side is a cluster from thinker, realist, feeler, and the right-hand side is I try to just group all those closest clusters to see, I just use a very simple k-means and see what's the main theme of the cluster. I find some cluster, their action is a trader. Some cluster, their action is a mindful or emotional investor. Some cluster, they are risk-averse planner. And I find that they match very well, like thinker is left-hand side, feeler is on the right, and the grandma, the persona is in the middle. The cluster is also a middle. So we find the agent exhibits heterogeneous preference when role play different persona. And we do see this can be a good benchmark or good matrix for us to train the large language model when they role play heterogeneous personas. So last, what we are going to do is an interesting experiment. I introduce blackout in the 10th of the day. We want to see how agents behave if we have some intervention. And we see the red curve is a blackout. At blackout, PhD use all the energy and the battery energy decreased dramatically. And after the blackout, they try to resume. And the distribution is just the end state of charge, the battery level by the end distribution. Grandma, they do the same thing. Grandma do the same thing, also discharge, but the energy at the end is slightly higher. Feeler is also higher for the energy by the end. And we want to understand the reason why. And the PhD just say they will reassess energy after blackout and adjust strategy just to maximize earning. That match what they do. And the grandma would say they want to ensure have enough energy for emergency. That's the reason the end SOC, the energy is higher than the case without blackout. And the actor is interesting, like the language they try to match actor. And I don't want to say this representing a true actor. I just want to say large language model give heterogeneous responses, and they change when we have blackout intervention. And this can help us to run the energy system because it's very difficult to collect data for those rare events. And we hope large language model can help us run some experiment in some low frequency, high impact case like blackout. So let me quickly summarize. We give a framework of the large language model to construct the behavior agent in dynamic energy system. And we try to answer how credible and realistic are these agents. And we say they do have more optimal and less variable behavior in different market conditions, and they have heterogeneity when role play different customer. And we do experiment of blackout intervention because we want to do behavior discovery in those low frequency, high impact events. And we see large language model can provide transparency into their decision making. They can explain why they change, and they also can carry memory over all the day for the reasoning and articulate how they act and the underlying motivation driving these actions. So this is the summary of my current progress, and our publication is here. So I'm happy to take more suggestions to see how we can move forward together in this field. Thank you.
Great, thanks, Song. That was fascinating. Just as a reminder here, we're gonna save questions till the end, so we'll move on directly to our next speaker, Yongchao.
Yes. Can you see slides?
Not yet.
Okay. Seems to be the glitch.
Okay, there we go.
Okay, there we go. So I'm going to talk about simulating different stakeholder perspectives in social ecological systems. And I would like to start my presentation with an image I found on social media, which is viral. This image shows a person watching the same wildlife documentary footage, but react totally different. On the left, this person is cheering for the lion catching the antelope, but on the right, he's distressed. So the same footage, different reactions. This is ironic, right? the most likely comment hit the points. It's all about perspectives. This insight is very important for our socio-ecological system modeling, where there are many diverse stakeholders, including farmers, NGOs, researchers, politicians, and citizens. All of them operate within their micro-environmental environments and observe, interpret, take actions from their own perspectives. Something beneficial for one group might be a threat to another, which often causes conflicts, policy deadlock, delayed actions, and so on, posing significant challenges to sustainability. Actually, in 1988, American philosopher Donna Haraway has already conceptualized this perspective problem. She coined the concept of situated knowledge, and she argued that all knowledge is situated, is created and produced from a specific angle, from a specific stance. And objectivity doesn't mean a third-person observer, doesn't mean if we take the third-person perspective as a system observer, then we naturally being objective. Instead, we need to take different perspectives. We need to embrace true objectivity through a perspective pluralism. This is her idea. So what it means for our modeling, that means we need a very different approach to understanding social ecological systems. Being an observer is not sufficient to obtain a systemic, holistic understanding, but rather we should step into others' throes, see through their eyes, and feel the feeling, tackle their challenges. And this is exactly the reason that motivated us to build a framework called HOPES, Human-Oriented Perspective Shifting Framework. This framework is, the overall structure is very simple. It contains two components. The upper the components out of LLM agents representing different stakeholders. They can interact, argue, compete, collaborate with each other, and they can influence policy implementation, which will be imposed on the environment. And the environment will give feedback information to the stakeholders. So this is a closed loop system. And human users can be an observer, of course, and they can also take a role here and change the role from one to another. After playing many roles, they can gradually gain the perspective knowledge and maybe can integrate different knowledge from different angles. So this is the main idea. This is our this is a prototype system we have built following this framework. This is one major. It has two major components. This is just one of them, called perspective taking simulation system. So you can see here is still a closed loop system. The upper part component is the is a institutional. We call it an institutional network, including all of institutional stakeholders. For example, the high-level institution and the lobbyists, including environmental NGOs, land use associations, and advisors, law consultants, and research suppliers, which can take information from the land use system, do data analysis, and inform other stakeholders to make decisions. And there are two operational institutions, which is environmental institution and agriculture institution. So all of these institutional stakeholders work together. They influence the land use system, which is called Crafty, developed by our group, and form a closed loop system. So the whole model is the core engine of our simulation system. Upon this, we build some interfaces. Interface one is responsible for example, row selection. We can select different rows, and we can set different time lags, how long after every iteration, every 10 iteration, you can adapt your policy implementation to influence the land use system. And you can confirm your settings and hit the run button to start the simulation. And also this interface will show some agent outputs here. Another interface is responsible for the interaction between the user this is the entry point actually, interfacing the user and the system. So the system can draft their decision making and generate a report and send this report as the final decision to in the system. This decision will be broadcast across the system, so everyone, or some of them, if you set up the visibility, can see the information. And also, this interface offers some AI assistance to help the user to explore the data, because sometimes the data set is too big, so many things distracting the user's attention. So maybe you need a convenient way to get the right information from the land use. And also we offer some conventional data dashboards to visualize data to gain some visual intuition. And this is the other part, the second part of the prototype system, which is an AI reflective learning companion. So there will be an AI assistant, actually is a facilitator. After you play a role, you can enter this system, and this AI companion can guide you step by step to reflect on what you have done, and what you regret about, and how would you want to improve in the next term, and what knowledge you can transfer from this role to the other role, something like this. And after the reflection, you can come back to this system to take a new role, play the same role again. So back and forth, this forms a perspective iteration loop. So that means you can play different roles. This is why we call it perspective shifting. Okay, if you feel okay, it's enough, and or I'm tired, so you can select to enter the next phase, which is called integration phase. So the AI companion will guide you to review what your conversation between you and the AI assistants, and integrate all the knowledge together. And eventually a formal report, structured report, will generate a structured report regarding your conversation and reflection process. So that's the whole system. Based on this, we did an early exploratory case study. So here are some important settings. A user who is interested in evidence-driven policymaking, the user choose to play the system observer, which is a default role for the role-playing system observer first, and then choose to play the research supplier here. This is a task-heavy role, because it has to analyze a lot of data from the system. And then there's a constraint, very important constraint. The research supplier, the user, has to be politically neutral. That means it can't lean towards to the lobbyists or to any of the operational institutions. Instead, the user has to offer politically neutral, but technically sound policies to influence the high institution in terms of allocating budgets between this agriculture or environment, and influence the high-level institution to adjust their policy goals reasonably. So these are some important settings. Here are some results. So as a system observer, the user noticed that the AI researcher, research supplier failed to convince the high-level institution because the AI did not provide strong and clear policy recommendations. Then the user stepped into the AI researcher's role and did some improvements. So the user provided clear numbers and use some adjectives like, for example, notable or radical to highlight the urgency to take big actions, to take some transformative actions. However, the user also failed to influence the high-level institution very effectively, because being politically neutral is disadvantageous. There are other politically non-neutral actors in the system, so they are more valued by the better institution, a high-level institution. So the user feel frustrated, and this person wants to improve the performance in the next role playing, because this is a task heavy role playing. So we didn't continue. We just stop here, and it's very early exploratory research. So in the next time, this guy said, okay, I want to highlight the bad consequences. Yeah, if you don't do this, if you don't adopt my recommendation, then something better will happen. So this is this motivated the person to change the narrative framing. So here are some interactive data. If you are interested, maybe yeah, the screenshot, the screen does not show the browser here. Here's some screenshots of the prototype system. It has different sections. We just can have a quick look at it. And we can select different rows here. And this is the row description. You can hit confirm button. This is just a part of it, actually. And this is some data dashboard to visualize data to facilitate the user's understanding of the land use system state. And this is another, this is also an interactive decision-making interface. This is a decision you have made, generated by the AI, of course, based on the communication with you. And here is editable. You can review the decision and edit before you submit the decision. Here is an AI that you can ask for policy suggestions, or you can ask it to visualize your data. It can, I give it the accessibility to my local files, so it can extract the JSON or the CSV file to do some data visualization for the user. And this is the reflective companion system. So you can, if you enter this system, you can start to reflect, and through the reflection, you can gain some knowledge, perspective, specific knowledge. So this is a very early exploratory research, and there are still many challenges. For example, stakeholders, how should we calibrate these AI agents against real-world stakeholders? This is the challenge lies in that the LM output is open-ended and prompts are very flexible. And the second one is how to evaluate the effectiveness of the simulations. Do users really learn? What if some users are immune to perspective taking? They just feel difficult to stand in other stance. So these are also the challenges we have to deal with in the future. And third, how to make the system more immersive. This is more about an human-machine interaction problem. And the last one is how to effectively analyze tons of text output. Yeah, we can, of course, use text mining, semantic analysis, or manual examination, or mixed. But there is no established framework to analyze this is not numerical, so it poses a new challenge for our analysis. And the next step is to solve about these issues, of course. Here is the paper preprint we submitted. And if you're interested, you can scan the QR code here. Yes, thank you. That's it.
Great. Thanks, Yongchao. A virtual round of applause for both of our speakers here for a great set of talks. We're going to move into discussion and Q&A now. And so the way we'll go ahead doing this is you can either input your questions directly into the chat box, or you can simply raise your hand, and we will sort of switch between hands that are raised for sort of live questions, and also looking at questions in the chat box. So we have Vivek, who is monitoring the questions as such, but we did want to kick off with a question from one of our co-moderators here, Stefano. So I'll turn it over to Stefano to start the discussion with a question.
Sure. Thank you, Jim, and thank you to the speakers. It was very enjoyable. I have a question regarding the behavior of these AI agents. So one might imagine that the behavior that these agents have, the potential biases they may have in decision making, their views of the world, etc., right, is influenced by the training data that have been used. And so my question for the both of you is, what kind of control as scientists do we think we have in terms of the training data that are being used and therefore the worldviews that these agents demonstrate? And in relation to that, what can we do when these behaviors might become ethically questionable? And thanks again.
I'm sorry, I didn't follow your question very clearly. Could you, yeah.
Sure. My question is, I guess, two questions. Well, the first one is, what type of control do we have in terms of training data and therefore the behavior that these agents demonstrate? And second, is there any ethical issue if agents start to behave in ways that are unethical?
Okay, may I answer first or?
Sure.
Okay, yeah, for the first question, normally we just use LLMs to build our agents, and we normally don't get involved in training because this is a very expensive process, and small models often don't work well. So we just use it. We use open source. We can deploy open source LLMs on our servers or just use the commercial ones. So in terms of the control over training data, so we really don't have too much power on that, I think. But we can still control the agent's behavior from different aspects. First, we can control its architecture, how we build the workflow inside the agents, whether it has a reflective loop to prevent its outputting from outputting something harmful. This is one thing. And the other thing is that prompt, of course, this is the most flexible way to control the agent's behavior, but it's most effective, but it's also challenging because prompts are open-ended and it's all textual. It doesn't follow the rules. It's instructive, right? It's not imperative. So we can't control the agents like we control rule-based agents or computational agents. This is really an issue. And the third one is that fine-tuning. Yeah, we can fine-tune LLMs. We don't train them, but we can fine-tune them. This is cheaper, but more effective. So if the agent outputs something unpleasant, maybe, then we can fine-tune it, but this requires some high quality and representative data set. So this is kind of laborious. Normally, I wouldn't do that. In terms of an unethical aspect, yes, this is a big problem. And I think there are already many researchers are targeting this problem. This is called a human alignment. So how we align LLMs with human values. Yes, there are a lot of methods and approaches have been proposed, but there's no established one. It's still ongoing research. Yeah.
Thank you.
Yeah, I agree with multiple part of Yongchao. Yeah, for me, I think just echo maybe some part is like when in context we can design the prompt saying avoid ethical response and provide more like a neutral perspective in your task. So starting from reasoning model, I find they follow all the constraints much better than the previous model. And I believe all those tech companies will also try to improve the large language model to follow the constraint instruction from the user. So I think the simplest way is to do that. But definitely some training, we can also prepare the data to avoid some biasing in the training data if we build our own RAG system to augment the large language model. So that is one part we can do for the training set. Yeah, just a short something added to it.
Okay.
Thank you.
And then I think we have a question from Dale Rothman. Dale, I don't know if you want to unmute and ask your question.
Yeah, sorry, I'm feeding a little one. So I had first for Cong on your talk, I noticed I couldn't identify what the users, what the players or the agents themselves. You talked a lot about their charging and discharging the battery, but I had no sense of how they were using the energy and what for. So could you say something about that? Were the users, did they have sort of a schedule of activities that used energy?
Yeah, thank you. I think you are starting with a very practical setting how people use energy. And I'm trying to think first test if large language model works a lot. If it works, we will move to more practical environment. And the way I test it comes from some story from the news. In 2025 at Texas, there are some startup company give free home battery to many households and say you can use the free home battery and whatever you like. But the company may collect some data and see what's the preference to help to improve their product design. And also I think in multiple years ago at Dartmouth area in New Hampshire and Vermont, they also do some similar experiment for home battery. So what I do here is also very simple, like I just assume large language model are representing those households. And then we say we give you a free home battery. You can use it for 20 days. After 20 days, I will take the battery off your home and we will analyze all this data, how you use your battery, how you react to different price, and what is the user preference. And my goal is like, this is a very simple experiment. If it works, then it's worthwhile for us to move on to use large language model for more complicated energy operation scenario. But if it doesn't work, then I think I will just stop and I'll wait for large language model to be better. Then we can run more complicated experiments. And my conclusion is with all those reasoning model from this year, we can run like some more like analytical task, and they can do some computations in those energy management scenarios. Yeah, that is like the background. I hope I answer your question. If you have anything, I'm happy to follow up. Yeah.
All right, I'll follow up because it was just like when they're discharging the battery, are they just selling the electricity back to the grid or are they
Yeah.
actually oh, that's what's happening.
Yeah,
So
yeah.
it's all right. That's all I need to know then.
Oh, okay, I see. Let me clarify. So the experiment design is when you charge, it charge from the grid. When you discharge, you have two options. You can discharge to the grid, but if it's blackout, when you discharge, they will discharge to your home usage. So I make the scenario very simple so that when they decide the energy is very simple outcomes. Yeah.
All right, thanks.
Thank you for your question.
Okay, and then Wenkang Jiang.
Yeah, thank you. I have a question maybe for Professor Chen. From my understanding and as it also is highlighted from the takeaways from Professor Yongchao, it's that the output of the large language model may be random or it's not so deterministic. But from your numerical studies, it seems it can give a very deterministic analysis. So I want to know if I missed something here, or can you clarify a little bit of this part?
Yeah, sure. So for my experiment, it's Monte Carlo simulation. So we repeatedly ran it multiple times, and we show the mean value and the variance. The variance is very big for GPT 3.5 or those older version. The variance is much smaller and controllable for the from 01, 02, 03, all those latest model. And so I think there's no deterministic setting in large language model. And for all those experiments, I believe we need to do repeatedly pumping and try to analyze the mean and the variance with Monte Carlo simulation.
Okay, maybe another follow-up is that have you tried to give more input along this process to improve their strategies, or just Monte Carlo simulation during your numerical studies?
I don't understand the more input part. So I mean,
if we interact with the current general large language models, if I want to, for example, improve some some sentences, I will give very specific structures. Okay, I want this sentence to be organized or something like that. I mean, during your experimental designs, it's only at the start I will give these kinds of things. If along this process, I will not give any other improvement strategies to help this large language model to maybe output better results, right?
I see. Yeah, thank you. I think some open source, I saw Yongchao tapped in the chat like, hey, open source the code. And I also put all my complete prompt in the appendix of the paper. So you can definitely see how we guide large language model in their response. We do provide a strict format saying you need to respond in this format. That way we can easier understand the result and parse the response into different segments. Yeah.
Okay. Thank you so much. Yeah.
Okay, and then Ellen Di Vittorio has a question about the AI companion interface for the land use model.
Yeah, hi, thanks. I was really curious as to how the AI companion interfaces with that land use model, right? It's based on the usage of it, it comes up with these policy scenarios, and then supposedly that feeds into how land use is allocated. And I'm just kind of curious what that, is that just an economic determination that's given to the land use model, or how does the land use actually allocation change based on whatever the policies are that are determined by the AI companion?
Yeah, we just use a very simple technique. We just ask the AI stakeholders, for example, the high level, the operational institution, policymakers, because they interact directly with the land use model. They just output in a very structured way in a JSON file. Actually, they should indicate how much tax or subsidies, for example, in percentage, to influence, to adjust the policy. For example, in this year it's like $100 for a tax, but next year it increased with like 10%. Then it becomes $110, something like this. So in this way, the LLMs it's an easy way for them to comprehend what is going on. Yeah, it's not something very complex mathematics there.
Okay, Kyung-Ho Sun had a question.
Hello.
Yeah, we can hear you, Kyle.
Okay. So I just typed my question on the chat. So let me see what I said. So your experiment using 20-day, so I wonder whether if you think that the 20-day experiment is sufficient to observe, energy use across the agent, or if you increasing or decreasing the experiment duration, how that agent behavior might change. Or I think that each agent may have different like memory length, like maybe some agents think like maybe much longer, the memory. So do you have any comment on this aspect?
Yeah, so first, I choose those 20-day depend on the optimal policy structure. The optimal policy for storage is first charge in low price, discharge for high price, and at the end just sell everything, leave empty storage by the end. So if we choose only 10-day or 5-day, they will start to sell everything immediately, and you won't say buy low, sell high first, and then sell everything later. So 20 days is a good length. We can see the complete optimal decision structure. This will allow me to use a math benchmark to understand the large language model decision. And a quick response for 100-day. 100-day, you can also see that, but as you say, we need to process longer memory, longer prompt, and we need a better way to manage the memory efficiency there. So that is a separate topic. I want to make the current experiment simple simple so that we understand the ability of current large language model before we move on to more complicated tasks. Yeah.
Okay, thank you.
Okay, and Christian Klasser.
Hey, thanks. Yeah, so I was interested, especially to Kong Chen, but now I have the feeling maybe it's might be relevant to both. What was your experience with trying to extract specific numbers, quantitative results from the prompt? Did you always do that throughout the experiments? In the first presentation, I was not so sure. Sometimes maybe the sell decision might be a binary, do I sell or not sell, depending on the price. And yeah, was this challenging to extract specific numbers? Did you have strategies, recommendations on how to do this?
Yeah, so for my experiment, I want to make it very simple. It's just like if you decide to charge, it's charge 1 megawatt, decide to 1 kilowatt, decide to discharge 1 kilowatt and do nothing, it's just nothing. So this decision is more easy to keep track of. And we also have a qualitative analysis. That is like we ask them to output reflection, write a journal, state in the memory. And we also analyze the embedding of all the response. So it's a textual embedding in high dimension. And we find they have those qualitative clusters showing actor, thinker, and also realist. They have different cluster, different preference. So this is like how we analyze those data, control the response. And I think large language model can output quantitative, like there are some experiment asking to play game and they can pick a specific number. And in that way, we also need a specific scenario design. And I think that is also doable in simple game setting. But all my worry is like if we move to very complicated practical application, we need to be more careful about how we construct the prompt and how we use the large language model.
Okay, so for you, it was a decision really to say we don't give the freedom to say 1, 2, 3, 4, 5 megawatt, but keep it simple.
It is, yeah.
Okay, thanks.
May I add some words?
Okay.
Yes, I think in terms of extracting quantitative data or more generally structured data, I would recommend using a JSON file, which many LLMs have been trained on. And there is a technology called, actually, this is a technique called constraint decoding. So this can largely ensure the structure of the output. This is something very useful, and in the past, it's really very annoying to have this output structured. But for now, I think it's a solvable problem. Yeah, and in the prompt, of course, you can also give the LLM agent some examples to show an ideal structure of your output, maybe a nested JSON file. But if it's too nested, it might make some mistakes. Yeah, this is my experience.
Thanks. I'm gonna look that up. That sounds like a good approach. Thanks.
Okay, and then I think to close things out, Jim.
Yeah, maybe one final question here that relates to Christian's question just now and Tungle's as well. So these were both like very nice, I think, stylized or kind of more exploratory analyses, exploring the potential of generative agents, which is, I think, given a very appropriate, just given sort of the nascency of all this. You know, in MSD research, we're often deploying what I call like high fidelity models of various sectoral systems. This could be something like a power systems model that's modeling the reliability of the grid under a certain scenario. Or on the land use side, this might be a model of land use change over the next 50 years, right, under different forces of change. And I'm wondering, like, if either of you have a vision for incorporating these generative agents in that world of modeling, or in that kind of form of scenario modeling, so to speak. What are the opportunities? What are sort of the critical challenges towards that vision? So maybe we'll hear from both of you on that, and then we can wrap up the webinar after that.
Yeah, I don't have very broad comments. For me, I start with curiosity. It's like I read a paper, I find, does it really work? And it is really a human simulator. I believe that's a big goal for people train large language model for. And large language model can be trained for very multiple purpose of applications. And we are just looking at one specific application. And my vision for my research is I want to build my research on suppose we improve the model better and better so they can follow the constraint more strictly, they can run some optimization, and they can process some data, use some tools, and how are we going to apply this much more better model into the practical world application. And we want to see the potential of bringing it in the energy application specifically. And my step is just like start with simple simulation first. And if it works, we increase the complexity. And now I want to say, I'm not going to replace all the human experiment. So we have human simulator, but it is more like a suggestion, something we can save more money, save more time, and we can run more experiment in parallel. And we still need some human experiment to validate if all those human simulators are working or not. Yeah, but mathematically, in all those computation, we can also test it to give us some suggestions saying, do we get valuable feedback from those large language model? And if it is a valuable simulation, helps us to improve all the, for me, it's energy management system, some energy policy, and the broader application, maybe some general policy. If they see a good feedback from large language model in the loop in all the simulation, then I think that's already a positive signal. Thank you. Yeah.
I think for me the most the biggest challenge to to applying LLMs in simulation is agent calibration or validation. Or I frame this problem as from web simulation to scientific simulation. So there are a lot of strange words. Let me call it strange words. Like who or cute, for example, in XAI's Annie, the AI character, right? That character has a very long prompt, but there are a lot of magic words, and how these magic words will influence our scientific results. This is still unknown. But this, of course, if we just use it in industrial or commercial applications to build some AI companion, that is fine. But if you really want to ground the agents empirically, then this should be some serious. This should be a problem that we really need to think about. And also, I would say LLM agents they are too open-ended. They are too spontaneous, and we can't guarantee the control over this agent's behavior. So how to ensure they really behave as we expected? This is also another challenge, especially in large scale LLM agents. You can't ensure that there is no crazy agent doing something that undermines your scientific results. Yeah, I think this is something, yeah, in my head, and this is a big hurdle actually that prevents me from applying LLMs in large scale agent based simulation. Yeah, maybe we can work together to solve this problem.
Great. Yeah. On that note, sounds like a lot of promise in this space, but also a lot of sort of critical challenges to think through as a research community. So with that, I want to thank the speakers again for all of your insights today. Thank everybody who joined and for a very engaging discussion. So with that, we will wrap up things and look forward to future webinars from the community. So thanks everybody. Have a great day.